Part 4 of Unit 10 is about reaction mechanisms. You probably remembered this page from video 10.1 where we said that for a reaction to happen, reactants have to collide with both the right orientation and right amount of energy for the reaction to take place. That amount of energy that's required is called the activation energy. There has to be enough energy present for a reaction to start. Just like a golfer can't putt a ball over a hill if it doesn't roll up the hill with enough energy. Reaction's not going to start unless the molecules have enough energy to get over that activation energy barrier. This graph right here is called a reaction coordinate diagram. It shows the change in energy over the course of a reaction. If you look at the axes, reaction progress, that's just similar to time as the reaction takes place, and energy is on the y-axis. This is our reaction. A yields B. So A is going to be the reactants, and B is the products. So what has to happen is the reactants gain a certain amount of energy, and this difference right here is our activation energy. At this peak, the reaction starts, everything changes around, and produces the products in the reaction, part B. So the difference between where the reactants start and the peak is your activation energy for the reaction, and the difference between where A and B start is your difference in energy, your change in energy for the reaction. This is an exothermic reaction because it's a negative difference. The products have less energy than the reactants did, so that energy was given off to the surroundings. An endothermic reaction coordinate diagram would end with the products higher on the chart than the reactants because they absorbed energy. The sequence of events that describes the actual process by which reactants becomes products is called the reaction mechanism. Reactions can occur all at once, or they can occur through several small discrete steps. Each of these processes is known as an elementary reaction or elementary process. So it could be several small steps happening that lead to an overall reaction. These are similar to what we did when we solved Hess's law problems. In a multi-step mechanism, one of the steps will be slower than all the others. The overall reaction can't occur faster than that slowest step, so the slow step in a mechanism is called the rate determining step. It determines the rate of the reaction. If we look at these two pictures, in the top one, the toll plaza A is going really slowly, so it's limiting the amount of cars that can get to toll plaza B. So toll plaza A is the rate determining step. In the bottom one, the cars are slowed down at B, not A, so B would be the rate determining step. Here's an example of a mechanism problem. We have the overall reaction at the top and the proposed mechanism for it below, the two steps that make up that overall reaction. Now to show how we get there, we're going to treat this similar to a Hess's law problem and see what we can cancel out from each side of the reaction arrow. So we've got an NO2 that can be canceled out because it's on both sides of the reaction arrow, and same thing with an NO3. There's nothing left to cancel out, so we just add up the rest and we're left with NO2 plus CO yields NO plus CO2. NO3 is what's called a reaction intermediate. It's produced in an early step of the mechanism and then used up later on, so it does not show up in the overall reaction. The slow step is the first step. That's called the rate determining step. Therefore, our rate law is going to look something like this. Rate is equal to the rate constant times the concentration of NO2, and that is going to be second order because even though we cross one of these out, there's going to be two NO2s in the rate determining step, so that's going to make that a second order reactant. CO does not show up in the rate law because it comes after the slow step, the rate determining step. So the reactants that are included in the rate law is everything up to and including the rate determining step, but none of the reactants after. So here's another example, overall reaction at the top and proposed mechanism at the bottom. Let's see if what we have to cancel out to get there. Well, NOBr2 shows up on both sides of the reaction arrow. So it's going to be, again, an intermediate. It's produced early and used up later on. So we're left with 1, 2 nitrogen monoxide, so 2NO plus Br2 is going to yield 2NOBr. There's our overall reaction, and to determine the rate law, we include the reactants, every reactant leading up to the slow step. So the rate is equal to the rate constant times the concentration of NO, and that's second order because it shows up twice in this mechanism. And then we're going to include Br2, and it'll be first order since it only shows up once. Let's talk about catalysts. We mentioned them first in video 10.1 and said that they increase the rate of a reaction, and they do that by altering the mechanism in such a way that the activation energy is decreased. So the red line in this graph represents the uncatalyzed reaction for the decomposition of hydrogen peroxide. It's got a higher activation energy, and when we add two catalysts to it, these two right here, the blue line shows the path of the catalyzed reaction. The activation energy is not as high as the uncatalyzed reaction, and it's not a smooth curve either. There's two extra steps going on because it's changed the mechanism of the reaction. What's important to remember about a catalyst is it goes into the reaction early on and is produced again at the end of the reaction. So if we were looking at a multi-step mechanism, a catalyst is a reactant in an early step and is produced as a product in a later step. It's the opposite of an intermediate that's a product early on and used up again later as a reactant. Neither intermediates or catalysts show up in the final overall reaction. Question for this section: consider this mechanism. Identify any intermediates and or catalysts present in the multi-step mechanism.